Today we're doing an introduction to binary search trees. First, here are some terms that are related but are important not to confuse with one another. So, binary search, a search algorithm for finding a target element in a sorted array. Binary tree, a tree where nodes can have no more than 2 children. Finally, binary search tree just sounds like a combination of the previous two terms, which it is. A binary search tree is a binary tree with the following special ordering properties. The left subtree only contains nodes with keys less than or equal to the node's key. The right subtree only contains nodes with keys greater than the node's key. This is true for any node in the tree. Sounds like there might be some recursion involved. Let's demonstrate the ordering property and validate this tree. I'll do an example with the left subtree, but the idea would be the same for the right subtree. For this example, imagine the current node is the black node. Any values greater will be blue, and any values lower will be red. So first, we see the black root node 4 is greater than his left child 2. Okay, now let's check the left subtree and make sure every value is less than 4. Our current node is 2. We see that 1 is less than 2, which would be also less than 4 by the transitive property. That's valid. And we also see that 2's right child, 3, is greater than 2, but less than 4. This left subtree is valid because it follows the ordering property. Let's discuss some neat properties about BSTs that result from their ordering properties. We can very easily find the largest and smallest element of any BST. How? Well, the largest element must be the rightmost node because in a tree with multiple nodes, the right child must always be greater than its parent. Likewise, a similar logic follows for finding the smallest element. The smallest element is the leftmost node. That aside, now, let's go over some basic operations like insertion, search, and deletion. For insertion, the idea is to traverse through the tree comparing node elements until you reach a node that has an empty link you can insert your child to as a leaf. Then, insert your node as a left or right child based on whether its key is greater than or less than its new parent. I'll show an example. Bam, here's this fully formed tree that I just made up. Okay, say we want to insert 5 into this tree. How? Let's start comparing with the root node. 5 is less than 20, so that means we must insert our node somewhere to the left of 20, in the left subtree. Let's compare with 20's left child, 15 now. 5 is also less than 15, so we have to check the left subtree again. Let's compare with 15's left child, 10. 5 is still less than 10, so maybe we'll have better luck with 10's left child, 3. 5 is greater than 3. Okay, let's check with 3's right child. We found a null spot where we can insert 5. So that's how you add a node. We went through the tree, traversing and comparing until we could find an empty space where we can insert 5 as a leaf. Next, we'll go to the idea behind the search operation in BSTs. Here's the same tree from before, except this time we'll find if a node with element 25 exists. Since this is a binary search tree, searching in a BST is similar to a regular binary search. Our root is the middle node, or middle value as well. So we will compare our target 25 to 20 and continue with the left or right subtree depending on whether 25 is less than or greater than 20. 25 is greater than 20, so let's compare with the right child, 29. 29 is greater than 25, so let's compare 25 with 29's left child. 29's left child is 25. Our target node's element matches this node's element, so we can safely say we found 25 and that 25 exists in this tree. I'll show a code example to demonstrate what this might look like in code. How does the algorithm we described before look in code? There's recursion. On the left, we have a method called getHelper, our search method. On the right, we have the same tree from before. I just added it for a bit of, visual clarity. So firstly, let's call our getHelper method with parameters root and 25 as our target value. Now going through the code step by step, we check first if our target is null in edge case. If it is, we throw an exception. Since our t-value is 25 and not null, we can ignore this. We also check if our node parameter is null. Our root is not null, so we continue. This statement will return null if the tree is empty or if you've traversed through the tree and the target does not exist. Next, we compare if our current node's data, in this case our root's data, dot equals our target element, 25. It does not, so we continue. Now we have to decide whether to check the left or right subtree. We check if our current node's data is greater than our target value. If it is, we recurse on the left child. Otherwise, we call the method on the right child. Since 25 is greater than 20, we will call this method all over again on the right child. Here's what the next recursive calls will look like. Once we get to getHelper 25, 25, we will return 25 because the current node's data matches our target's data. Moving along, let's discuss deletion. Deletion's a little trickier, and there's 3 scenarios that may occur when you want to remove a node. Here are the 3 scenarios. If your node is a leaf, we will set the parent's link to null. This is the simplest case. If your node is a node with one child, we will set the parent's link to the node's child, thereby effectively skipping over the node we want to delete and removing it. If your node is a node with 2 children, we must replace the node with its in-order predecessor. This is the trickiest scenario, so let's go over examples for each case. Here's a new tree. Say we want to delete 96. Let's first locate it in the tree. Okay, so 96 is a leaf node, meaning it has no children. Recall case 1. If our node is a leaf, we simply set the parent's link to null. Bam. 96 is gone. All we did was just set 29's right child link to null. Alright, let's go over deletion case 2. Say we want to delete 3. Let's locate 3 in the tree. 3 is case 2 because it has one child, so we set parent's link to node's child. As you can see, we skipped over 3 and thus have removed it from the tree. Now, let's go over the trickiest scenario. Say we want to delete 20. We locate it. And it's the root. In this BST, the root has 2 children. This is case 3, so we need to replace our node with its in-order predecessor. An in-order predecessor is the leftmost node in the left subtree of a node. Its value, if you organize all the nodes in ascending order, would be before the target node. In this case, 17 is our in-order predecessor. Let's replace the root node's data with 17. Okay, now we can remove 17. The removal of 17 here is case 1, so we simply set 15's link to null. In the previous this example, it was nice that we could remove 17 so easily. But what if the in-order successor has children? The answer is recursion. We'll use multiple cases to maintain ordering property. Alright, let's do this one more time. We'll attempt to remove 20 again. 20 is the root, and to remove it, we need to find its in-order predecessor. Case 3. Now, to remove 17, notice it has one child. This is case 2, where we set parents link to 16, skipping over 17 and removing it. And then we can set our root node, or the node that we wanted to remove, and replace it with 17. Voila, we've deleted 20 and replaced it with 17, its in-order predecessor, and I've also maintained ordering property by setting 15's right child to 16, 17's original child. To conclude, let's discuss some time complexities. Trees are bound by O height time. Here's a table that shows the time complexity of BST operations that we went over. Notice that there are different results in average case and worst case. In average and best case, all operations are log n time. Recall that log n is the height of a balanced tree. But notice in worst case, time is O(n). This is because of skewed or unbalanced trees. In a skewed tree, all operations take O(n) time. Think about it. If we wanted to search for 1 in this tree, we'd have to start at 24, the root, and then compare with 1 with 24, then go to the left child, compare 1 with 6, then go to the left child, compare 1 with 2, go to the left child, and then we'd finally find it. We had to go through every node. We couldn't just, like with good binary search, break it in half. Because there was nothing to break in half, it was just a line of descending values. Alright, that's it for today's episode.